Hi, my name is Van, and this is a presentation on refraction. And specifically, we are going to be examining the common demonstrations used to back up the claim that refraction can effectively allow an observer to see beyond the geometric curve of the Earth. So here we have a very well-known photo of the Chicago city skyline, and we are told that in this photo, we are not actually looking at the physical buildings. We are looking at the effects of refraction because the buildings are roughly 60 miles away from someone standing on the shore, and you should not be able to see that far according to the globe curvature formula, curvature rate. So this is the claim we are examining that refraction can cause this effect. In this presentation, I'm going to focus specifically on examples that introduce a second medium. And that would be image formation at the boundary interface. And that's what I want to talk about and what I've learned about recently that I think is important in this conversation, because the demonstrations used to prove this claim that refraction can bend light around an obstruction as so we can form an image, the observer can form an image. This claim, these demonstrations are often used to back up that claim. And I think they are not analogous to the claim they're trying to back up. So these pictures here in this demonstration are from our good buddy Jesse Path of Light, and I got them from his YouTube channel, and I thought it was a decent demonstration of what we're about to see here. So a camera is looking out a window, and it has line of sight to a house that's across the street. And Jesse has put this obstruction here as so it's physically blocking the house that is behind it. And then he adds a prism to the top, which is a secondary medium, and then all of a sudden the house is refracted around the obstruction. And I think he even used this rounded opaque obstruction at the bottom here to represent the curve of the Earth. And so this is a demonstration showing, hey, look, refraction can bend things around the curve. But what I hypothesize is going on is something very specific to the introduction of the second medium. It's not analogous to refraction within a single inhomogeneous medium. This is specifically when you add the second medium. So here's a little ChatGPT definitions here, and I just want to define image formation at a boundary interface and talk about it. So image formation at a boundary interface is the creation of a real or virtual image due to the change in direction of light rays at the surface separating two optical media of different refractive indices. So we have image formation is the creation of images due to the change of light rays at the boundary between two different media. That's what image formation at the boundary interface, and it's specifically because of the change in direction of light rays. So and I'll talk more on that, but the boundary interface here, it says the physical surface where the refractive index changes abruptly, e.g. air, glass, air, water, etc. The key word here is abruptly. So the light is going from one medium with a refractive index, and then it's entering another medium with a different refractive index. So there's a jump, there's an abrupt change, and a change in the direction of light rays. So I think that is very significant when talking about refraction. This effect happens specifically at a boundary interface. It does not happen within a single medium. So here's just a quick diagram. We have the two mediums, and it's showing the boundary interface right in the middle. And so medium one could be air. We have the incident ray coming from the top left. This is the light ray. from the object or whatever. It's hitting the second medium. This could be the prism in our case, a prism or water or something. And so it enters the different medium, it hits the boundary interface, light abruptly jumps to the different refractive index, and it is at that boundary interface that an image is formed specifically. So here's another example that I took at my apartment with my sink, and this is just highlighting the boundary interface again. We have a sink, we have an observer looking down at the sink, and the drain at the bottom of the sink is obstructed by the lip of the basin. But when we fill up the sink with water and remain at that same angle of observation to the sink, the drain reveals itself. It has lifted up to our eyesight, and this is specifically because of the boundary interface. So the light comes from the drain in the water, it hits the boundary between the water and the air, light jumps refractive indices, it changes abruptly, and then that which allows for a virtual image to form, which we can see. If I take it one step further and I keep filling up the sink with water until the whole bathroom is filled up with water from the floor to the ceiling, and the observer's in there too, this is what I think he would see. There would be no boundary interface, and this is just to highlight how it's the boundary interface specifically that is causing this refractive effect. This refractive effect does not happen within a single inhomogeneous medium. So quickly, I want to just define an important term, which is inhomogeneous medium. So an inhomogeneous medium is one in which the refractive index varies smoothly with position. So we're talking about air, or the atmosphere. It has a density gradient. It is an inhomogeneous medium. So it varies smoothly with position, for example, with altitude in the atmosphere or depth in water. So unlike refraction at a sharp boundary interface, like air glass, there is no discrete jump in the refractive index of n. Instead, n changes continuously through space. So this is highlighting that within an inhomogeneous medium, there is no, it's a smooth, continuous, gradual path that the light is bending. There is no sharp change, therefore there is no image formation. So here's a quick just diagram of a light ray bending in an inhomogeneous medium. In the middle you see the darker region is the denser part of the gradient, and you have light rays coming, like the top light ray. It's entering the medium, it's in the medium, and it's traveling down gradually and continuously toward the denser medium. So this is just how the light ray behaves within an inhomogeneous density gradient. And so here's just a couple more quick examples. This one's not the best, but I got this from Jaren's channel, and this is someone filming the display of a camera, so that's why it's a little wonky. But what we see here is that what they're showing here is a ball, and from this vantage point you cannot see anything on the far side of it. But when he puts a glass lens in front of the ball, then the pin or whatever on the other side of the ball is revealed. So this is just another example of adding a second medium, creating a boundary interface, which creates that virtual image because of the sharp bend that the light travels from different refractive indices. So I think this is the final slide, and I'll just end on this. This is a little meme I got from New Perspective, but in all these examples here, what needs to happen to show, we're talking about the claim of light bending around an obstruction, aka the curve of the Earth, and so it's an obstructed object that we are forming an image of, that is supposedly being lifted around the obstruction of the curve of the Earth. So that's the claim. But these examples, and all these examples, they are not analogous to the claim, and they are used as um, evidence of the phenomenon. So in all these examples, a second medium is added, which creates the boundary interface, which allows for a virtual image to form due to refraction. So I think that's what's happening here, and I'll just end it on that. Thank you.